Yeah, good morning. This is Subramanya Surao, Professor, EC Department, Sasi Institute of Technology and Engineering. I am dealing signals and systems subject. Yeah, in the last class we have seen various operations that can be done on signals. Now this week we are going to start classification of systems. First, let us start with systems. Already we defined at the beginning of the subject, system is a physical device, a black box that can perform some operation on the input signal and gives a modified signal as output. This is symbolically we can say it as y of t is transformed version of input. So if we give an input signal, it is transformed by a particular operation that is indicated by t and gives a modified signal as output. So we can say that simply y of t is the transformed version of the input signal x of t. Okay, that we have seen. This is the basic for classifying the signals. Yeah, these are the different classification of signals: continuous time and discrete time. Similar to the signals, the first classification should be continuous time and discrete time system. Next, static and dynamic systems, causal and non-causal, linear and non-linear, time invariant and time variant, and stable and unstable system. Let us see one by one in detail, because for any student, classification of system is a foundation topic and is also parallelly important for exams. Yeah, first, continuous time and discrete time system. As we know what is continuous time and what is discrete time signals, it is very easy to define the system. A continuous time system is one which allows a continuous time signal as output and which gives a continuous time signal as output. Very easily we can define. No in-depth concept is there. So it is symbolically denoted as y of t is the transformed version of x of t. Here the input x of t is continuous time and y of t is also continuous time. So that's why the system which accepts, which processes continuous time input and continuous time output is called continuous time system. Very easily we can define it. Similarly, we can extend the same concept to discrete time. Discrete time system, it is an example for a continuous time system where input is given, our speech voice. At the loudspeaker also we hear the same speech signal. So that's why same signal, both signals at input and output side are continuous time. Similarly, we can define discrete time system with the same concept. A system is said to be discrete time system if it accepts a discrete time signal as input and if it generates a discrete time signal as output. Very easily we can show it with the equation y of n equal to transformed version of x of n. Here x of n is a discrete time input, y of n is a discrete time output. Both input and output are discrete time. So we can call it as the system as a discrete time system. Next, let us go one by one to the in-depth. So second classification is static and dynamic systems. Here it completely depends on a system. What is the foundation for the next 2 or 3 classifications of signal is, classifications of system is, system we are going to analyze the output y of t. Y of t at a time t. We are going to see the response of a system at a t may depends on the input, at present values of input, past values of input and future values of input. The next 2 topics depends completely on this: past values of input and future values of inputs. Now we are going to assess only the present output. It means output at time t. It may depends on the input x of t at t or past values of t and future values of t. Isn't it? As we have completed classification of signals and operations on signals. So for y of t, y of t, x of t is present input. X of t minus 1, x of t minus 2 are past values of inputs. Whereas x of t plus 1, x of t plus 2, t plus 2 are future values of input. Future values, these are past values, this is present values of input. Now we need to see whether the output y of t depends on present input or past values of inputs or future values of input. Based on that, we are going to define whether the system is static or dynamic and causal or non-causal. So first, coming to the static system, very basic one. Here we are going to see whether the present output y of t or response at time t, present output y of t should depends only on the present input x of t. Then the system is said to be static, isn't it? So static system means present output y of t depends only on present input x of t, but not on past values of input, but not on future values of input. Then the system is said to be static. We can easily recognize the static system either in continuous time or discrete time. See, let us see some examples. Y of n equal to 2 into x square of n. So here x square of n, here input at present values n depends only on the present values of, or output at present value n depends on present values of input only. N to n correspondence is there. Similarly, you can see another example in continuous time. Y of t equal to x square of t. Here also there is a t to t correspondence. Output at t depends on input at t only, isn't it? Or you like this, we can see a number of examples for it. Now you can easily understand by discussing dynamic system. If you see dynamic system, on the other way, a system is said to be dynamic if it also depends on either on past or on future values of input. Then the system is said to be dynamic. Suppose in this example, the present output at t depends on past values of input. These are past values of inputs. So dynamic. Similarly, here in this example, the present output at t depends on present input at t and future values of input. T plus 1, t plus 2 are nothing but future values of input. So here present output depends on present input and future values of input. As it depends on future, we can consider it as dynamic system. Like this, you can take n number of examples. So static means present output depends on present input only. Other than this, if the present output depends either on future values of input or on past values of input, then we can say that dynamic system. Very easy to understand and remember. Okay, that's about static and dynamic. Next. Next, let us see some problems. So here the first signal in continuous time, y of t equal to x of t minus 3. Suppose if you take a t equal to 0, then y of 0 equal to x of minus 3. Now we are at 0, but output at 0 depends on input at minus 3. For easy remembering of this, you can take an axis, t or n axis, traveling from left to right. So let it be 0 is here. So it is going like this. For 0, minus 1 is past. For 0, 1 is future. So let us consider that we are traveling from left to right. If we are at 0, already minus 1 is over, so it is past. If we are at 0, 1 did not reach till now, so that's why it is future. Like this you can remember, it's not a technical rule from any book. It is just for remembering easily. So output at 0 depends on input at -3. So past values. So it is a dynamic system. It's a dynamic, very easy to remember. Present output depends on past inputs, so dynamic. Similarly, y of n equal to x square of n. You can take any value. Suppose y of 0 equal to x square of 0, or you can take y of -1 equal to x square of -1. So output at a particular time depends on the input at that particular time only. So it is static system. You can take another example, y of t equal to x of 2t. Here also it is somewhat difficult to tell whether it is static or dynamic directly by seeing the equation. So it is better to substitute some values. Suppose if we substitute at t equal to 0, y of 0 equal to x of 0, here the condition is satisfied. Present output at 0 depends on present input 0, no problem. But if you take a t equal to 1, y of 1 equal to x of 2, here the condition is not satisfied. Here output at 1 depends on input at 2. For 1, 2 is future. So here for positive values, the present output depends on future values of input. So here again it is a dynamic system. Dynamic system. Last, you can easily tell, because n plus 2, n plus 3, n plus 4 are future values of input. Here the present output n depends on future values of inputs. Present output depends on future values of input. So it is also dynamic. So this much easily we can recognize it. Here without doing, you can easily tell. Here the present output depends on differentiation of x of t. Ultimately it's not a direct one-to-one relation. Differentiation of means at some other time it depends. So here also it is a dynamic system. Like this we can do. That's about static and dynamic systems. Next. Next, second one, causal and non-causal system. A system is said to be causal. It is the continuation of static and dynamic system. A system is said to be causal if the present output y of t depends on present and past values of input. What is the present input for y of t? X of t. What are the past values of inputs? X of t minus 1, x of t minus 2, like this. If the present output y of t or present output or response of a system depends on present values of input and past values of input, then the system is said to be causal. Okay, it is simple extension of static and dynamic system. And these systems are physically realizable systems. So all the practical systems available in nature are generally causal. It means, we can switch on the fan only after switching it on. If we switch on at t equal to 0, it will run after t greater than 0. So it means it is a physically realizable system. So all causal systems are physically realizable systems because they exist at t 0 and greater than 0. So see, you can easily see here the present output at t depends on present input at t. So it is a causal. Similarly, in the second example, present output at t depends on past values of input and present values of input. T minus 1, T minus 2 are past values of input, whereas x of t is present value of input. So present output depends on past and present values of input. So it is also a causal. Similarly, you can take here in discrete time, the present output depends on past values of input and the present value of input. So here again it is causal. On the other hand, we can define non-causal system. A system is said to be non-causal even for one value of t or n. If it depends on future values of input, then the system is said to be non-causal. It means if the system depends even for one value on future values of input, then the system is said to be non-causal, which is exactly opposite to the causality. Okay, and these non-causal systems are physically not realizable. It means you can easily understand running of a fan before switching it on is the non-causality. Okay, causal means running the fan only after switching it on is causality. So that is physically realizable. Whereas non-causality means before switching on, if fan runs, that is not physically realizable. You can see the example. Here, present output at t depends on past values, t plus 1, t plus 2 are future values, present and future. So, even for one value, if it depends on future, that is non-causal only. Similarly here, present output depends on present input. Up to this it is okay, but it depends on future values of input. So, the system is said to be non-causal. Yeah, let us do some problems on this causal and non-causal system. First, continuous example, y of t equal to x square of t plus x of t minus 4. So for easy recognition of causal and non-causality of a system, better substitute t equal to 0, some positive values of t and some negative values of t. Let us do that. So first, at t equal to 0, substitute it, y of 0 equal to x square of 0 plus x of 0 minus 4, minus 4. Now you are at 1. For 0, now you are at 0. For 0, 0 is present, minus 4 is past. Minus 4 is past. Already try to remember, if you are traveling from left to right, now we are at 0. For 0, minus 4 is already over, past. For 0, minus 4 is past. So here for t equal to 0, the condition is satisfied. Next, positive values. For t equal to 1, y of 1 equal to x square of 1 plus x of minus 3. Minus 3. Again for 1, now you are at 1. For 1, minus 3 is past. Here also the condition is satisfied. Similarly, you can take some more positive values. Similarly, you can take one negative value. For t equal to 2, one more positive value, y of 2 equal to x square of 2 plus x of minus 2. 2 minus 4 minus 2. Again, for 2, minus 2 is past. So, for all positive values, the condition is satisfied. Next, let us see for negative values. For t equal to minus 1, y of minus 1 equal to x square of minus 1 plus x of minus 5. Minus 1, minus 4, minus 5. Now you are at minus 1. Now we are at minus 1. For minus 1, minus 5 is past. So here also the condition is satisfied. Like this you can take some more negative values. So it is observed that for t equal to 0 and positive values of t and negative values of t, here the present output depends only on present input and past inputs. So the system is, present output depends on present and past values of input. Past values of input. So the system is causal system. System is causal system. Like this you can easily tell. Finally, let us see one more example. We can apply the same way. Substitute first t equal to 0, y of 0 equal to x of 0. Here present output at 0 depends on present input. So condition is satisfied. Next, at t equal to 1, substitute one positive value, one or two positive values. Then it will be y of 1 equal to x of 1 by 2 means 0.5. Here now you are at 1. You can take the same concept. Now you are at 1. For 1, 0.5 is passed. Already over. So at t positive values, the condition is satisfied. No problem. Similarly, you can take one more value for t equal to 2, y of 2 equal to x of 1. Here also, now the output it is at 2 depends on input at 1. For 2, 1 is already over, passed. So here also the condition is satisfied. So for positive values, no problem. Now let us take some more negative values. At t equal to minus 1, y of minus 1 equal to x of minus 1 by 2. It means minus 0.5. Now try to think of it. Now you are at minus 1. This is, let it be, this is minus 1. Where is minus 0.5? Here. This is minus 0.5. As we are traveling like this, you are at minus 1. Minus 0.5 is future. It did not come till now. So that's why here the condition is not satisfied. Causality condition not satisfied. It depends on future. Like this you can check for one more value. For t equal to minus 2, y of minus 2 equal to x of minus 1. Again for minus 2, minus 1 is future. It did not come. Now you are at minus 2. This is minus 2. For minus 1, it is future value. So I hope it is easy to remember this logic for easy understanding of causality. So for all negative values, the condition of causality is not satisfied. So the system is non-causal. We need to conclude that for negative values of t, the condition is the present output depends on future values of inputs. Future values of input. So the system is non-causal system. The system is non-causal system. Like this, we can easily do the causality problems. Yeah, that's the end of the class. In the next class, we will cover remaining classification of systems. Thank you.